Well, thanks very much for having me. It's last day of a meeting which I also found very interesting, and thanks, like everyone, thanks Boumediene for the relentless pursuit of these kind of meetings, and also all the online talks and stuff like that he organizes. It's a really huge enterprise. Good. As it's Friday and we're close before lunch, I'll talk about something which is somewhat different than what most people seem to have been talking about. Even though it's quite a big theme, I think, in learning, is so-called equivariant learning. Yeah, so according to some people, somehow this is a really important aspect of the success of learning, is to kind of like understand how to be efficient and not compute more than you need to do by taking into account so kind of like a so-called equivariance, which is basically some kind of symmetry property of the system. So, but let me first emphasize this is joint work with Victoria Klein, who's a PhD student, and Kevin Webster, who's at Imperial College. And there's some support from EPSRC for these kind of things. Good, so normally my bread and butter research is not this, so bear with me. I also noticed that the number of references that I put in the talk is below par, so if I was my own PhD student, I would really be somewhat critical. But so most of the things that I will talk about are not so much original in terms of content, but I think they're maybe original in terms of approach. So it really has a sort of kind of like a flavor. Anyway, so the background is symmetry, and I used to study physics, and then I did some kind of dynamics with symmetry and so on. So I was like well brought up in some of this, and now the thing is not working. Yeah. Good. So just on the philosophical point, maybe we can handle that on Friday morning. So what's data science is, in my sense, is some kind of giving meaning to bags of numbers. The problem with the data science is just have an enormous amount of numbers, doesn't really know what it is. So methods that don't seem to kind of try to find structure in just bags of numbers has a low chance to be successful to give any understanding. And of course, meanings are applied by models that we then use. So in some sense, every technique we use has a schematic model. And this choice of the model is very important, and I'd like to just emphasize that because, of course, different types of models can answer different types of questions. So I'm sometimes a bit baffled by the fact is that we all seem to kind of agree what the model is before we know what question we want to answer. And sometimes it's a problem, because sometimes we get something out of the model which actually can't answer the question we want to answer, and then people start, yeah, the model is okay, but the interpretation of the model then isn't. Anyway, so I think that's actually quite a key point in all of this data science. And people, of course, have been thinking about these things a lot. So one of the important things is that we have some mathematical structure in our model. And I think the structure is key to the interpretation and the meaning of the modeling of the data somehow. So we use, of course, certain types of models, and they come in because we've dealt with them positively in the past. We know ODEs, we know certain types of PDEs are very popular because we could solve them one day by hand, and they were so efficient and so great and so on and so on. And now we have computers, and we have difficulty solving PDEs on computers, for instance. So we should ask ourselves also whether we should be doing these things. But one of the important things is that most of this mathematics has been developed in some kind of quest to do data science and physics. Because there's like observations, to start maybe with planets and so on, and you know, hundreds of years of observations led to at some point people understand what the planets are doing. And in some sense, there's data science, of course, not with computers, but otherwise. And people have appreciated somehow this quest, of course, there's a lot of structure in mathematics, and it's mostly motivated by this purpose somehow. So the objective was not, I think, to kind of like just use data instead of other mathematics. It was actually some kind of like having the data, you try to kind of understand what are the regularities there and find the right mathematics to describe those. And so when we do data science, I would say at least to expect to see a whole list of mathematical topics in data science appearing regularly. So here listed here, analysis, probability, topology, geometry, and algebra. I hope I don't really, I probably have missed out some very important things here, but this is one arbitrary list that is quite broad. So in some sense, if you look at applied mathematics, it seems to be coming more or less from the top to the bottom. A lot of people here do analysis, some probability, maybe some geometry, algebra. If I look from physics, I think we're coming from the bottom up. In theoretical physics, algebra is really, really important. Algebra is the stuff that classifies things. That we have a finite number of elementary particles comes from algebra, not from analysis. There's a lot of structure. So if we want to structure observation somehow, we want to classify things, the question is like, are we here or are we here or are we somewhere in between? Yeah. So of course, for some kind of questions, maybe algebra is not so important, but I would say algebra is really a workhorse of physics. So of course, there's this kind of physics-informed and geometric learning, and these are kind of quite successful. So what is the aspect here is that of course people use particularly kind of certain types of PDEs. So you say like, okay, we know already more or less what the things what we're looking for. So maybe that's not too broad, or explicitly use geometric structures, like for instance, variational structure or symmetry, right? So this is usually called under this kind of geometric deep learning and stuff like that, physics-informed learning. So the role of algebra historically came through, most pronounced through Klein's idea to say that basically most of geometry can be formulated in terms of algebra. And what was the idea? The key idea basically, and this was hugely successful, and what he did, I think it's on the next slide, but it was one of the advantages of algebra is that it deals with equalities rather than inequalities. I would say that's something that we also should think of when we compute. So estimating things and finding upper bounds, lower bounds, and whatever. The nice thing of algebra is often that something is equal, and that's also why we get like finite numbers of elementary particles. We don't get an upper bound and a lower bound and something in the middle. And it of course has this huge tool. So if you do theoretical physics, then often you spend most of the time doing some kind of algebra. And for instance, the representation theory of groups, and it gives classification of particles, energy structures of atoms, and the energy band spectra in solid state physics, structural properties of molecular spectra. If you want to see whether your fruit is rotting somewhere, you shoot some laser in some room, you pick some things under the band structure tells you which kind of molecules you see. So I wrote here, algebra remains to play a subdued role in machine learning. Of course, this is modulo linear algebra in some sense. So of course, linear algebra is also very nice. And we use it all the time, right? Because you can do things with this. Yeah, when I was preparing this, I thought about so there's no Dutch people, I think, here in the audience. Are there Dutch people here? No, there's some very strange song which says, you know, how do I benefit from algebra? It was a hit in the 1970s in the Netherlands. Actually, the problem here was that the girl wanted to use algebra to sort out which guy was better as a boyfriend, but it's a different thing. But anyway, the question is like, how can we use algebra in the things? Yeah, so the key shift in the Erlangen program is to rather than try to describe the geometry of a surface by describing the surface, to describe it by the transformation that leaves something invariant. And that gives you basically the kind of like algebraic objective, because apparently what you can do is you can classify these transformations, and they have a lot of structure and can be captured by algebra. So the symmetries, they admit a concise algebraic treatment. And this, in turn, enriches our understanding of the geometry, so in some surprising way. So examples here, representation theory. So if you say like, how do certain symmetry groups act, then we know that if the group satisfies some mild conditions, so for instance, there is a compact Lie group or something like that, then which means that basically it's kind of most of your groups are of this type. Then you have a finite number of type of actions of this group, and they can be calculated by hand. It's a finite calculation in terms of some matrices and stuff that you can use some linear algebra and something to calculate and classify the number of equivalent ways in which a group can act. And that really then gives a lot of rise to a lot of important things in physics, like for instance, you have a finite number of elementary particles in certain type of theories. Another theory is important, singularity theory. If we have some kind of complicated surfaces and we have singularities in them, we ask like, how many types of singularities can you have? Well, could be quite wild, but by singularity theory, we find out that basically certain singularities appear much more often than others, and the trick is that we can formulate this problem in the fact that when we see a singularity, we know it's very well approximated by some algebraic singularity or some polynomials. And this really gives you a way to classify some of the singularities, which is also the basis of bifurcation theory, for instance. And invariant theory is another important thing, is the functions that are invariant under some kind of group actions. And the question like, can you kind of classify them? And it turns out also that there's a nice theory for that. So these are just examples. And so some of the things are often in say kind of like applied, say, physics courses, or so representation theory should be in any decent physics course. Singularity theory, less so, but also quite popular. Invariant theory doesn't seem to appear so often. It's a bit more hidden, just are not usually in textbooks. Okay, so why am I saying all these things? Because it's been well noticed, not by myself, but many others, that in machine learning task symmetry naturally arises. And it's also kind of important, and it really speeds up a lot learning. So for instance, computer vision was often uninterested in the orientation or position of parts of the image that needs classifying. So if you have a dog in a picture, you don't really care where the dog is, you don't care which orientation it is, if it's turned around or whatever. If we want to classify a flying object, we want to know which airplane it is, we don't really care maybe what its position is or what its orientation is. But the good thing is that if we are aware of symmetries, we can also actually kind of code these things very well. So for instance, if we have, say, a flying object, an airplane, we can say, well, we can try to first learn what is the airplane. That's an invariant object with respect to orientation, rotations, and stuff like that, and translations. But I maybe also want to know where this airplane is and what orientation it has. And that's again encoded in some symmetry properties, because I want to know what symmetry transformation, which isometry do I need to get to this airplane. And that's also something you want to learn. So there's this underlying geometry is useful and maybe really a key to what you want to do. Good. So another important topic, I think, is I've seen people work on this, is understanding invariance properties of things. You see an object and you ask, is this a circle? Is this a sphere? Is it something else? Is it an invariant? So this is basically close to the decline things. Like if we see an object and we want to identify it, rather than maybe just try to fit it with something, maybe we just want to find the transformation that leaves it invariant. Now, if you look at dynamical systems, and this is also well known in dynamical systems literature, if we want to understand properties of dynamical systems, their symmetries are quite important. Why? Because general dynamical systems behave very different from dynamical systems that have certain symmetry properties. Now, of course, if you're used to certain kind of equations, then it's more or less obvious because it's inherent in the equation. So, for instance, some kind of PDEs have very naturally some kind of like Euclidean invariance, because it doesn't really matter for your Navier-Stokes whether you rotate things around or you translate things around. But it does actually make a huge difference for the dynamics that they generate. So once you try to kind of learn something and you know that your process has inherent symmetry, it will be a very good idea to learn something that has the symmetry, because that's something that should inherent have. If you don't, then you get some approximation that maybe breaks the symmetries, and some of the symmetries are essential for the behavior. So you get very, very poor approximation from models if you get the wrong symmetries. You have of course classical mechanics, we know with Noether theorem, we have invariant momenta and all kind of other stuff, and people don't like it if you learn a mechanical system and you get all these things wrong, because all things look very different than the textbook. Yeah, so this is also important in things like molecular dynamics and molecular discovery and material science. So a lot of AI companies work on this kind of like thing to try to kind of compute a lot on these things, and they use a lot of equivariant machine learning because they know the structures of their molecules and stuff like that, and they really want to use it. They don't want to they want to get the right symmetries. They want to use the symmetries also in their computation. And another point that I want to tap on, which is important, is that if you do reduction of problems from very high dimension to low dimension, we also want to kind of have good representation, well, of many properties, but one of them could also be symmetries. For instance, if we know that a high dimensional problem, something should have a natural set of transformations that's important, some isometries, for instance, and we are interested in those, because maybe there could be symmetries, or if we have a latent representation, what we want is that also these isometries have a good representation in the latent representation. So not that I have just a high dimensional space, I just chunk it all down in a latent representation, I lose all my structure. If I lose all my structure, my latent representation really doesn't do much for me. So if I have an autoencoder or something like that, that could be a real trouble. So it's not just the structure, it could also be metrics, of course, it's important. We want to, if we have metrics in our real world, how does the metrics project to the latent space? Good. So what about this equivariant learning and what have people done? So the most intuitive approach to equivariant learning, if you say, well, we want dogs and we want to learn dogs and cats in all, but we are worried that we get something wrong, that if you rotate a dog, that you don't recognize anymore it's a dog, then you just augment your data. So it's really it's kind of level one thing. You say you have a data set. I think that my task is invariant on some group, so I just augment the data. I just let my group act on all the things, and I produce thousands of dogs in all kind of orientations, and I hope that my machine learning algorithm somehow learns that it doesn't matter what the orientation is of the dog. So that kind of works, but of course it's kind of at a huge cost, because your data set will increase a lot. Another one is loss-induced structure enforcement. So that's also people do in other contexts. So rather than actually inherently say that there's a structure in your problem, you say, well, I'd rather my problem has some structure, so when I kind of optimize, I'm going to give a penalty for not having the structure. So I hope it's a bit like some kind of Lagrange multiplier. I hope that some constraint is satisfied. So I put it in the loss. Now the advantage for these things is that you can just use generic algorithms, no problem. The disadvantage is that can be quite expensive in the first instance. Second instance, of course, you don't really satisfy this constraint in this way, right? Because you try to minimize it, but in practice you don't get really exactly the structure. So if you really think that the structure is important, that is not so great. Good. Yeah, so then there's another branch which has to do with maybe this observation that people say that machine learning is so successful, especially CNNs, is that we have some kind of a natural approach is then to say if we learn, we maybe inherently want to make sure we learn in an equivariant way. So especially for pictures, CNNs, so CNNs basically have this kind of sliding windows, and what it does actually, it tries to make sure that it doesn't matter what the orientation of the picture is, and you learn the picture basically invariant with respect to the translations. And so this is specific architecture be very, very successful. It's sped up enormously learning from pictures and video and all kind of other stuff, and vision, computer vision. And there's some generalizations of this, so-called GCNNs, group CNNs by Cohen and Welling and stuff like that. And also graph neural networks where there's a permutation symmetry implied locally in the graph. And what you do is basically you design an algorithm, you hardwire the symmetries in there in some sense. And then you get a model which at least to better approximation is hardwired to be obeying some kind of like symmetry properties. Now, an issue here is that if you look at these symmetry propositions here, is that they're not entirely exact often, because what they involve is some kind of like, how do you make something symmetric? It's, the big trick is to kind of just basically use convolution, but what's convolution? Convolution is basically just some averaging. You average basically over some group action. So what happens is you have some kind of network with several stages and a lot of layers, and you say, well, something has to obey some symmetry property, then every step of my learning, I have to make sure that it obeys the symmetry property. So what happens is that every layer we average over some group. So is a Z2 group, so reflection, then it's just everything over two elements in some ways. If it's SO2, then it becomes kind of a horrendous computation because you have to kind of basically take a whole circle, whole rotation circle. But people do this because people have big computers, so they say it doesn't matter. But this is the state of art in some sense. People use this CNNs, GCNNs, and they are very computationally demanding because you basically, at every step that you want to enforce the symmetry property, you do that, basically imply this by convolution. Yeah. So the advantage here of this method, the structure is intrinsic. Disadvantage is that, yeah, also for every group, somehow we have to think about how to do this. So that's, graph neural network or the CNNs, GCNNs, and it's kind of pretty inefficient. So I think efficiency is something also that is increasingly important. We all want to do things on our laptop and not buy some time at Amazon or Google to do a little problem. Good. So what is now the idea here, which is it's a low-hanging fruit, I would say, is to use algebraic structured equivariant learning. And so the idea is now to use invariant theory, which exists. It's one of the great achievements of Hilbert, to calculate systematically kind of equivariant functions that behave well with respect to symmetry actions. Yeah. So why is that? So this exists. So people thought about this basically in the beginning of the 20th century or maybe late 19th century as well, clearly. Coming from this Erlangen program to try to understand if you have a function that's invariant, how can you kind of characterize this function? And in primarily polynomial functions. So it turns out that this algebra is very nice, and there's a good theory of that. So if you say you have a function that behaves well with respect to symmetry, then you know what this function is going to look like. And this can be treated algebraically, can all be computed. So the advantage is, and we'll see that, is that we can use this theory to now kind of basically give constraint on functions in terms of these generators. And once we do this, it will turn out that we can actually use our favorite functional approximators. And we don't really need to worry so much about things because we will see that we have a modular structure in these functions, and some of the functions, just general functions, we can just approximate it with any functional approximator we like. So we don't need to really worry so much about the things. The only thing we need to worry about is to understand what the structures of these functions and how they are generated. Okay. Good. So advantage here is that the structure is then, and I'll show you how it works, is still intrinsic. You don't need to do the averaging. And so what's interesting here, so averaging is a technique that people use in these algorithms in the algebra to understand these functions, and you will see that there are basically something like finitely generated rings of polynomials and stuff like that. They also use averaging. But the good thing is here you only do it once. You only do it once, you generate all your objects, and then you just say, now I have all my objects, and now I can compute with those. Yeah. So there is an averaging going on, and there's an aspect, but you can do this symbolically. And you also, because it's the algebra, you can actually find the right answer exactly. So you don't need to do approximation. You can really do this, right? It's a one-time cost. It's architecture agnostic, etc. You get kind of a lot of nice, good things. So a disadvantage is that we then, of course, have to do this algebra. But the good news is that we have computer algebras, but they're not necessarily well set up to do this problem. So typical kind of problem that I could have here is I have like some kind of big data set, 1,000-dimensional representation. I have some symmetry group acting on this, and then I want to kind of do some algebra at this high-dimensional level. And unfortunately, most of the algebra was developed in principle in a nice way. But then if you do this very high-dimensional things, you end up using enormously kind of like expensive and long-winded algorithms, because most of these algorithms were written in the beginning of the 20th century. They are used to prove something. They're not used to compute something. And then in the books by Hilbert, Weil, whatever, you can find some by hand calculations. Of course, you can do in half a page your favorite example, but these are not 1,000-dimensional objects. So if you want to do the things on a computer, you have to be a little bit smart to see, can we actually kind of compute these things? And that's an interesting challenge, I think, also for computer algebras, is at the moment I think they're geared to kind of implement things that were done in the past and comprehensively so you can do more intriguing example, but there's also some kind of curse of dimensionality using computer algebras, and the question is like how can you speed these things up and do things really high dimensional. Good. So let me now just kind of do some technicalities. I'm running a little bit late. So an equivariant function, sorry, this should be f from x to y, is a function in such a way that it commutes with a group action. So that means that it does, if I do a group action on one side and then do my function, I know precisely that it's the same thing as doing first a function and then a group action. Now these g actions here that are about little g's, they act differently potentially on x and y. And I'd like to write it here as general transformation. It could be, of course, a linear transformation, but it doesn't need to be. You just have some group actions on manifolds, for instance, and then of course this is not linear. But there are some natural settings where G is linear, and that's where the algebra works. And for instance, if you have a function space on some ambient space Z, and G acts as this induced action, then we always have nice linear actions on that function space. So we have an infinite dimensional function space, but we have linear actions, and that's a very natural setting. Another one is where if we have a compact point group, so a group action fixes a point, then locally we know we can find coordinates that actually this all looks linear. Yeah? So there are settings in which you can just assume that we have linear actions, and that really facilitate the analysis. And if not, then we're in trouble a little bit with this kind of methods. But in the machine learning, we have a very often this kind of setting where we basically have an implied action on a function induced by an action on an ambient space. So if G acts trivially on Y, then we call the function invariant, because then we basically say that if we have a function f and I act on G on the input, then it doesn't matter for the output. That's an invariant function. Good. So linear group actions are referred to as representations, and as I said, there's a whole theory about representations called the representation theory, and we now assume that this group will act linear on our spaces, and then we can do this representation theory, and that's also important for basically this Hilbert stuff on invariant theory. So here's a kind of key theorem, and so if we have a function which is equivariant between some now linear vector spaces x and y, and let them be say finite dimensional for the purpose here, practicality, then what we have is that this function is written in terms of a general function that has the components of which are invariant. And these invariants, they're finitely generated. It's a polynomial ring which is finitely generated. And some functions fi, and these fi are equivariant functions. So the invariant functions, they don't see, if you do G act, it just gets absorbed, they just stay fixed. And here you get the right action on the output. This is the output of this is a scalar, and this is basically some kind of like transformation. Yeah, for the function. And this is finite, so everything is finitely generated. So I only need to know a finite number, and the finite number of these things that generate this pi of x. Pi of x is a finite set of generators, and I need a finite number of these ones. And so in the algebra, there's a theory that tells you upper bounds of how many of these things you would need to find. So it's basically some kind of finite search. So what is the so the approximation result. So it's an equality for polynomials, and then by Weierstrass approximation we can see, of course, we can do anything. So what if you want to do machine learning, you don't want to take this polynomial. You want just here a general smooth function of the invariance. It just gives you much more flexibility. So we can think of the approximation model as a general smooth function of something in certain coordinates times these things that makes it equivariant. Now the interesting thing of these functions here, you can also think of them as features. So these generators of group invariant functions, they're like features. It's like you have some of the right coordinates for your problem. So if you now want to learn this function f, it represents something of your interest, and of course the only thing you need to do is you just learn the p's. There's a finite number, s here, of functions, and the rest is just fixed. Yeah, so, and the input now, okay, the input gets filtered through these features because you learn it goes through the invariants, but it doesn't really matter. You just learn the function as a finite number, or input of a finite number of variables. Yeah, so that's that's pretty straightforward if you can compute these objects. Now, so why people haven't done that yet at large scale, it's probably because it just lies across a boundary where people just don't know these things. So there's a lot of people that try to use representation theory, because I think that's basically in the undergraduate textbook. And then people say, well, if you look at equivariant operators, you can think of them first do good coordinates, so you have a nice extensive symmetry group. That's basically what representation theory tells you. But then they don't use this, and that of course simplifies your problem. So good coordinates always simplifies your problem, also for this kind of structure. But yeah, people seem to not really use invariant theory for these computations. So here's just an example. So we have a d4 action on the square. Then d4 is a fourfold rotation and reflection, gives you the symmetries of the square. And so any function from R2 to R2 that has the symmetry is well approximated by a function of this type. So here are the two invariants. So all invariant functions are generated by these ones. And here are two independent equivariant functions. So you see, if you now want to learn this function which has a symmetry property, it's pretty easy. You just try to approximate P1 and P2 with your favorite approximation method. Good. Yeah, okay, so I said some things already. So what's the practical use? It's you just need to learn the function P. That's easy. These sets pi and the capital F's can also be computed symbolically. But of course there is something that maybe the computer algebra, yeah, if you put a generic, actually invariant theory is quite popular. So people like Stoomfels and so published things in the 90s. So people use invariant theory more, but equivariants are not in the usual computer algebra literature. So if you go to Magma, so you cannot really find an algorithm that generates those. There was a person, Karin Gatterman. She actually wrote a lot of software for this kind of things, specifically for equivariant bifurcation theory. And that's also how I am aware of this. Unfortunately, she's no longer with us, but that code actually, so Victoria Klein, she actually kind of like upgraded this code and she implemented everything in Python. So all this kind of stuff works now again. But it's not so easy to find. So maybe that's one of the other reasons that even if you know about this theory, if you cannot really just online compute these things easily, it's maybe not so easy to do. Good. Yeah. So the challenge is if the number of generators scale badly with dimension. But the good thing is that already Weil, a long time ago, figured out that if you have very, very high dimensional representations, and then there's some kind of efficiency you can see. So the invariant, the generators of invariants are not just generally, there are many of them, but they have some structure, and you can use representation theory in some sense to understand that they are related to each other. Yeah, so not so surprising. So if you have a very high dimensional representation where essentially the representations are low dimensional, but just many of them, then there's some efficiency you can do. And so-called multiplicity reduction. My impression is that it's not been done that well. So there's some things that in theory work, but it's maybe not the best thing yet. And then you can, also use sparse linear algebra methods for the computation of these things. Good. Here's, for instance, an example that it says that if you have some representation which is many copies of the same representation, and it often happens actually like that, because it may be essentially a small thing, but if your resolution is big, you get many copies of the same kind of action. And then there's a way to kind of understand that we can essentially work with generators of low dimensions transformed in some kind of ways, in linear ways, with things that respect the symmetry. This formula doesn't really tell you so much. It should tell you somehow that there's an intelligent way of doing this if you think about it carefully. Good, yeah, so in this computer algebra, there's quite a lot of things that still could be done better. There's problems with this kind of like Grobner basis stuff and so on. Some of these routines run very long, and you have to check at some point when you have a generating set. And there seems to be that there's some inefficiencies there in this computation. So you want to kind of get one to it, but you have to go through another route to kind of to get there. So this is still possible to do better. And maybe that's another kind of plea that I would like to make here, that if you think about machine learning, we should think of machine learning not only in functional approximation and stuff like that, but also in terms of using computer algebra better. Yeah, computer algebra is another workhorse that we can use in machine learning. We can generate lots of interesting objects that have meaning with computer algebra that we cannot do by hand, that we should use that to do our task in a better way, and not to say, well, we don't care and we just kind of approximate it in other ways. This is not so smart. Good. So here's an example. Just kind of to say, you know, it is not a super challenging example, so I apologize in comparison to many people that are more professional about this kind of thing. So what we try to do is we learn some 2D Navier-Stokes flow from some pictures, and we try to do it in a way which has a symmetry. And here we take the symmetry to be only D4. So ideally you want to do it Euclidean symmetry, but it just we haven't done yet. So it's kind of work in progress, but it's just more like a pilot to see that it can be done and how you should do this. So you just represent this picture in a certain way, and then what you do is you identify a certain action, because there's a natural action on a picture, and if we think of this 28 by 28 pictures, it's a small picture, and we have this group action, so this has an action on a vector of this length, but still kind of very high dimensional, because it lives in R28 squared. So we have an action of D4 then acting on a very high dimensional space that maps this picture around in a certain way. And now what we want to do, we want to find a low dimensional representation in terms of which we want to understand the dynamics. But we want to regain this kind of symmetry properties in this low dimensional representation. That means that I can actually, if I have my picture, my flow, if I want to rotate it or reflect it, I can just go to the latent space and I know exactly what transformations I have to do. So what you do is you build that in. You make a kind of an encoder in some sense to the latent representation where you just enforce an equivariance property. You make sure that the picture that comes in, if you would rotate it, that in the latent space it also rotates in a certain way. Good, so how do you do that? You have to choose an action on your latent space. It's not given. It's not. So of course we chose here that it's the latent space has m dimensions, and we have with m is even, and we have then m divided by 2 copies of a 2-dimensional representation of D4. It turns out that there are other representations of D4. The regular representation has dimension 8. There are three different representations, irreducible representations. And then what you do is you learn this function. So we now use this structure, and this property will say that basically we try to use we try to use a latent space, and this latent space of course has to be invariant with respect to symmetry. So there were some talks earlier where people say, oh, we want to do some linear algebra computations, and of course you also then want to have good basis and not your operators mapping you outside your finite dimensional space. And on the computer we need to be finite dimensional, so you can systematically kind of like choose this. So what you want to do is you want to find a good basis of functions that represents these pictures well, with 28 parameters, and also in such a way that if I make some transformations on this space in the real space, which is 28 squared dimensional, that it goes to this 8-dimensional space also in the correct way. So I can kind of do these things properly. Okay, so once we have done that, we have the space, and then we learn basically the latent flow in the low-dimensional space just using a neural ODE of some type. And again, I don't claim any sophistication at this level. Yeah, so you can just do this. Good, so now that was important here because we had such a high dimensional representation that we couldn't compute with computer algebra in its 28 square dimensional, 398 dimension, the invariance, but we can do it faster using these results of Weil, and then we can learn the dynamics in this latent space, basically, where we now have a much lower dimensional representation, and then everything is everything is also kind of automatically kind of like equivariant because everything is written in the right form. Okay, so then we did some computations, and here's some pictures. Maybe here's a zoom. So it's supposed to show that everything is okay. So the first we learned the first 5 from the first 5, and we expand in the next 5, and this is with a relatively low dimensional representation for this kind of like order 2D flow. Of course, we want to do it better and with higher symmetry group and so on. So this was more like a pilot study. So the main take-away message for this is that think about algebra, how algebra can help you. I think algebra is a friend of a computer. It fits. You can do symbolic computation, and really, I think it's really not well enough explored. So it's not that no one uses it, but it should be used a lot more, and especially for this equivariance problem, because this is supposed to be important accelerator of machine learning. So we should use it in the best possible way. Okay, thank you, and have a good lunch soon. Yeah.